Hi everyone, welcome. My name is Omer and I'm really happy to be here today and talk to you about a subject that is important, beautiful, and close to my heart, and that is the internals of Git. Now, how many of you have used Git? Great. How many really understand what's happening when you use Git? Okay, cool. So we have a lot to learn. And let's start with a few questions, just to get a feeling of what we're going to talk about. Okay, so what happens when we git commit? So actually, when we hit git commit from our CLI, or we do it with some UI, what's happening under the hood? More specifically, on every commit, what is being stored? Is it the difference between the current commit and the previous commit? Is it the entire work in dir, or something else? When we start a new repository and we hit git init, what actually happens? Now, we may ask ourselves, these are really nice questions and all, but I mean, why do we even care? Why should we care about these things? It's how things work under the hood. Isn't it enough that we just know what command to use and how? So basically, I think there are a couple of really good reasons to understand how Git works. One is that we're professionals, and as professionals, we should understand the tools that we use, especially when it's tools that we use every day, like Git. Also, it's really cool, at least for us geeks, it's really cool to understand how things work. And it can also be practical. For example, at Swim, we apply knowledge regarding Git internals to how we do things in our product. So this talk is going to be an introduction to Git internals. And we can't talk about everything about how Git works in 1 hour. But after this talk, you will have all the foundations you need to understand what's happening most of the time and to go on from there while you read additional resources. And how is this talk going to work? So after a short introduction, it's going to be hands-on. So we are going to build a repository from scratch without using commands such as git init, git add, or git commit. But before that, we want to make sure everyone is on the same page. So we'll start with an overview, and then we'll gradually zoom in on specific things. And I promise everyone will learn something new. OK, so let's start. When we start, we need to first understand the different objects that Git has. Now, it's really useful to think about Git as a system for managing file systems, and specifically a system for managing snapshots of a specific file system in different time frames. What is a file system? So basically, a file system has folders and files, right? It usually consists of a root directory. In Unix-based system, we usually mark it like so with a slash for the root directory. And within this directory or folder, we also have other directories and files. So for example, it can have user and bin as folders, and these folders may have subfolders or files, textual or binary files. So we have directories and files. Now files include data, right? A byte stream, actual data. And it also includes some metadata. For example, a file knows when it was created. So even if you take the file and you move it to a different folder, the file remembers, that is, it carries the information of its creation date. Now in Git, we have a rough equivalent of a file, and this is called a blob. Blob stands for binary large object, which is just a stream of bytes. So this is only the data, not metadata. This is different from file systems that contain metadata for files. So it could be just a byte stream. It could be textual data, which is, of course, also a byte stream under the hood. And again, blobs, the equivalent of files, have just data. And every blob in Git can be referenced by its corresponding SHA-1 value. So SHA-1, a hash function that we run on a stream of bytes, and we get a value. The value is 20 bytes long. Usually it's shown as 40 hexadecimal characters. Now in this case here, I'm only going to use the first 5 characters because, well, otherwise it would just be too long on the screen, okay? But it's going to be 5. Remember, it's basically 40 different characters, or 20 bytes. Now, if I were to write the same file on two different systems, exactly the same files, would they have the same blob shards? Yes. Since it's the same content and I run the same function, I'm going to get the same SHA-1 value. So I can reference a blob or a file in Git, a blob, by its corresponding SHA-1 value. So if in a file system the equivalent of a file is a blob, the equivalent of a directory is something called a tree. And tree is just a directory listing of blobs or additional trees. So this one, for example, says we have the blob with a SHA-1 value of F92A0, and now it has a name, pic.png. And we have another blob, 73D8A, this one, which is called 1.txt. So we reference the content of those files by their corresponding SHA-1 values. So a blob is an object in Git, and a tree is also an object in Git. And if it's an object in Git, it means that it also has a corresponding SHA-1 value. Cool, so now we have a tree, again, the equivalent of a directory, with two files. Now let's say this file system also has another file, this one here. Also has some SHA-1 value. And this is another tree that includes a folder, this folder called docs, and this file, test.js. And this would be the root directory of this file system. So we have the tree, which is the root directory, and it links to a subtree, a subfolder, and a file, and then to two other files. Cool. So again, this one would have a SHA-1 value, and we have the equivalent of files and of directories. But I said that Git is a system for managing snapshots of file systems, right? So a snapshot in time in Git is called a commit. So that is what a commit really is. It's a snapshot of the entire working tree at some point in time. So basically, it has a tree and some metadata. So for the tree, for example here, this one, it's actually the tree of the root directory, right? And then we can go from this tree to the other trees and files that it references, span and get the entire working tree or the entire snapshot of the file system. We also have a commit, a parent for every commit with the exception of the first commit. So this one is the first commit, so we don't have a parent commit. And some metadata, for example, who the author was, and some message. All right, so this poses a question though. If a commit includes the entire snapshot, doesn't that mean that on every commit we're going to store a lot of data, like the entire working tree, the entire file system on every commit? So let's consider this case. Let's say I want to change only this file, the one we call 1.txt, which consists of hello world, and I want to add an exclamation mark. So, oh, and of course, commits also have SHA-1 values that we're used to seeing, right, in git log, for example. Cool, so I'm going to add an exclamation mark now to hello world. So what's happening now? So I added that exclamation mark. What is going to change as a result? Yep.
There'll be a diff, and then you'll add the new file with the differing line.
Okay, so for this, yeah, correct. But now that I stored it, okay, what is going to change in this graph here? Right, so the hash value is going to change, correct? Because we have different content, it's a different hash value. Now if this hash value changed, it means that also this tree has to change, right? So we change this value here, and as a result, also the SHA-1 value of the tree object changes. So this one changes as well. And as the SHA-1 of this tree changed, also the SHA-1 here has to change. And as a result, the hash of this tree object changes. So this changes too. OK, so we got a lot of changes. But do I really need to store this object again? No, why not? It hasn't changed. We still have this object here, and we can reference it by the same SHA-1 value. So this is the trick. Whenever a file or a directory that is an object hasn't changed, we can just reference it using the same SHA-1 value and store space. Now, as a short disclaimer, in Git there are additional optimizations, for example, pack files to allow storing not the entire snapshot every time, but for now it will be much easier to think about it as Git storing the entire snapshot with the exception of objects that we already have stored in the past. Cool, so after we changed these corresponding SHA-1 values, we create a new commit object with a new tree. The parent is now of the previous commit. We have a different author, a different message, and we can compute the SHA-1 value. Cool. So we've seen 3 different objects in Git. A blob, which is correct, a series of bytes, binary large object, contents of a file. We have a tree, which is
Directory.
correct, a directory listing that can consist of blobs and other trees. And lastly, a commit, which is
Trees and subtrees.
right, and a snapshot of the repository at some point in time, right? So these are our 3 objects. Now another very prominent term in Git is that of a branch. And a branch is actually something really, really simple in Git. A branch in Git is just a named reference to a commit. That's all. What does that mean? So let's say I have a branch now called main. So it's basically a pointer, and later we will create it ourselves. We'll see it's just a simple file. It points to a commit. That's it. Now let's say I want to create a new branch called test. So I'll use git branch test. What would that create? An additional pointer, correct? Pointing to the same commit. So now that we have 2 different branches, and I'm going to commit, to create a new commit, on which branch will that commit be added?
Test.
Test? How do we know? Right, but how do I know from this drawing here? Well, currently I don't know. What we still lack is some way for Git to know which branch is the active branch, right? And for that we have something called head. Now head is also just a reference. And it points to the active, most of the time, branch. Head could also point to a commit directly, but almost all of the time it would point to a branch. So now we have head pointing to main, pointing to this commit here. And if I were to switch to a different branch using git checkout or git switch test, what I would do is actually change the value of
The
head, correct, to point to test. So if I'm using git checkout test or git switch test, that's all I'm doing, changing the pointer. And now if I were to use git commit does 2 things. It's create a commit object that points to a tree, as we learned, right? So we have a new commit that Daniel authored. But git commit not only creates the commit object, but it also moves the pointer of test to point to the new SHA. So even though I'm going to rewrite it here, draw it here, what happens to head? Where does head point to after that?
Test.
Test, right, so it hasn't changed. Okay, that was just a trick to make sure we understand everything. Head hasn't changed. I just moved test to point to the newly created commit. Now let's say I git switch main. What would happen now?
Head switch.
Head would be
Main.
main, correct. So I'm changing the pointer of head to main. And now if I'm creating a new commit, so I have Anna creating a new commit now, so the commit would point as its parent commit to that commit, B2424. And we'll change the value of main to point to the newly created commit. What about head? Hasn't changed, right? Still pointing to main. Cool. So a branch is only a named reference to a commit. That's it. Again, we'll create one ourselves in a few minutes. Cool. So now we know what a blob is. A blob is the contents of a file. We know what a tree is, a directory listing of other trees and or blobs. And we know what a commit is. It's a snapshot of the repository at a certain point in time. And we know what a branch is. It's a named reference to a commit. With that knowledge, you know almost everything you need to know. We need to apply this knowledge. But one more thing that's important to understand before that is the process of recording changes to Git. So in Git, we basically have 3 different snapshots. The first one is called a working dir, or working directory. Also, sometimes you'll find it as a working tree. It all means the same thing. Now, a working dir is a folder, a directory, on your file system that is associated with a repository. And it usually has, or it always has, one subdirectory within. Do you know which subdirectory a working dir has? It has one called .git. Today we'll understand what's happening there, at least some of it. It can also have other folders and files, of course. And what makes it a working dir, again, is that it's associated with a repository. Now, what is a repository? A repository is a collection of commits and other things, such as branches and head. And each commit is a snapshot of the working dir at some point in time, right? So a repository is a collection of commits and a branch, and of course head that need to point to that branch. Sometimes some other things as well. Cool. Now within Git, which is by the way different than most other version control systems, we also have a third state that comes between the working dir and the repository. And this is called either the index or the staging area. These 2 terms are interchangeable, and they're used widely in Git's source code, documentation, tutorials. So I'm going to use them both so we feel comfortable with both of them. And the index, or the staging area, are our playground to preview the next commit. So it allows us to take some of the changes from the working dir and apply them to the index, and then commit only these changes. So let's say I created 2 new files now in the working dir. And I'm staging only one of them. So I took this one and I included it in the index, but another one in the working dir. So currently the state of the working dir is different than the state of the index, different from that of the repository. Now if I commit now, what we do is we take the state of the index and we create a commit object to match that. So this is commit 3, and if I created a new commit object, what else would happen as a result of git commit?
Point to commit 3.
Correct. So main will point to commit 3, and we don't change head. So far, so good? Cool. Let's clear some space. And let's create a new Git repository ourselves. And we'll do it the conventional way, that is using commands that many people feel comfortable with. So let's start with git init. Okay, to start a new Git repository. Let's call it my repo. So I've created a new directory. If I use dir here, it won't show anything because this folder is hidden. So if I use dir/a, I would see .git. And if I'll use the tree command, I can see that it actually has quite a lot of things inside. We'll understand some of them in a few minutes. But for now, let's just create a file. So let me create a new file, echo hello into file.txt. So right now, it's only here, right? It's in the working directory, not in the index. If I want to add it to the index, what should I do? Git add, correct, file.txt. So if I use git status now, it will tell me you have one file to be committed. So I've staged this file, right? And now I want to create a commit object. So I'm going to use git commit and provide a message. So initial commit. So I created a new commit object. If I use git status, it's clean, nothing to commit. Git log. We have an initial commit. We have head pointing to main. Basically, we got this state. Cool. But that was easy and didn't really test our understanding of everything we've done so far. So what I want to do now is I want to try to create all of this from scratch. So let's clear. And let's try to create a new repository. So I'll go to a new repo. This is a new folder, and I'll try to use git status. What would happen? Fatal, not a git repository. Right, so a git repository has, as we know, a .git folder, right? So let's create one. That's a .git folder. Cool. Here we have .git. Tree .git. Okay. Git status? Fatal, not a git repository. Okay, so having a .git folder is not enough. Now, what does a .git folder have? Basically, a repository has two things. It's a collection of objects such as blobs, right? Trees and commits. And it's also a system for naming those objects. So let's create that. So within Git, I'm going to create Git objects to store the objects. And also refs, which is where we'll store the references to those objects. And specifically within refs, we'll also have Git refs heads, which is a Git internal name for branches. Cool, so I created those folders just to be sure. Now within the .git folder, we have an objects folder, we have a refs folder, and within refs, we have heads. Okay? Yeah?
Is it case sensitive?
It is case sensitive. Yep. Okay, and now let's try to git status. What do you think? Fatal, not a Git repository. Okay. So if you were Git and you were to start trying to see something about the repo, where would you start from what you know of how Git is constructed? How would we start? Yeah. Head. Cool. So we need to go to look at head. So let's create head. Now what is head? Head is a file. So I'm going to write into head. Head, you're now pointing to a ref at refs heads main. I'm going to give the name of a branch. We're going to name it main. And I'm going to write it into .git head. So just to be sure, we're clear on this. .git folder now has the objects and ref folders and also a file called head. And if I look at the contents of that file, it says refs heads main. Git status. Whoa. Git status on branch main, no commits yet. Cool. So we have a Git repository. What about git log? Fatal. Your current branch main does not have any commits yet. Okay, so Git is right. We don't have commits, but we do have a current branch main. By the way, have we really created a branch main? No, we just told Git by writing into Git head that the active branch is main, even though such thing doesn't exist yet. Okay, so we need to create a commit object, but we're going to do it from the bottom up. So what do we need in order to create a commit object? From our knowledge, what do we need?
Hashes of trees and blobs.
Right, we need a tree that would reference a blob, let's say. Okay, so let's write a blob. So let me write something. So I'm going to write brief channel. That's my YouTube channel that includes a lot of information about Git internals. Is awesome. And I'm going to pipe that into a Git command called hash object. And I'm going to tell it to take the input from stdin, from the standard input, that it take this and pipe it into git hash object. Now if I do that, what would happen is that Git would run the hash command on that file and give me the hash result. But I wanted to also write it into the internal object database of Git, so I would use -w. So what I got is a hash, a SHA-1 value. And let's see what happened within the .git folder. Okay, so under the objects directory, we got another directory and another something. Looks like a file. Does anyone recognize those characters? What do these correspond to? Right, so 8e is the first byte or first two characters of the SHA-1 value. So what Git does here is to take the SHA-1 of that blob we created, take its first byte and create a directory, and then the blob itself is included in a file whose name is the remaining characters. And why would Git do that? So in a repository with one object, it doesn't make much sense. Okay? But let's think about a bigger repository. Let's say one that consists of 20,000 objects. And now you need to look for an object by its SHA-1 value. And you have 20,000 different objects. To start looking would take a while, right? So Git basically divides that problem by 256 by taking the first 2 bytes, 0 through FF, creating those folders. And now if you have a SHA-1 of 8E, FF, and so on, you first look for the folder 8E, which is a much smaller space, right? And then you look for all the SHAs that start with 8E and only for the remaining characters. So it's just an optimization for the lookup of Git. Cool. So what did we create here? So I'm not going to use git add or git commit, but I am going to use other what's called plumbing command by Git, internal commands that are used by Git internally mostly. So I'm going to use a command called git catfile. Has anyone used it before? No, it makes perfect sense. But after today, you're going to feel comfortable with it. So git catfile gives me an option to look at the internal object database of Git. And I'm going to ask Git catfile -t for type. What is the type of this object? I can use the entire SHA-1 value. I could also use, oh, sorry, I didn't copy. OK, so let me write 8E FFF. I can also use, in this case, even 4 characters. It would be enough. And Git tells me this is a blob. OK, the type of this object is a blob. If I use git catfile -p for pretty print, please show me the content of this blob. Then I get the content brief channel is awesome. Cool, so I've created a blob. Is that enough to get a commit? No. Is Git status impressed? No, right? Nothing to commit. The fact that I created something in Git's internal database doesn't really affect Git status or anything. So in order to get a commit, what do I need to do now? Sorry?
You need to add it to staging.
Add to the index, right, and create a tree. So to add that to the index, I could use git update index. And I'm going to tell it to add a new entry with the cache info of this. Now, this doesn't really matter for me for now. These are Unix bits for marking that this is a regular file rather than a symlink or anything. Not really crucial for us. And now I would want to use the entire blob SHA. So let's select this. So I'm selecting this. Cool. And I'm going to give it a name, right? Because if it's a tree, the tree listing includes the name. So let's call it brief.txt, for example. Tree git. Is there anything here different?
Index.
Right. So we do have an index entry here, which means that the index is actually a file. Let's look at that file, .git/index. Doesn't print so nice, right? So we may need other commands to investigate if we want to, but it's just a file. Cool. So now what I want to do with this index is create a tree object out of it. So for that, we have the command git write tree. What this command does is take the state of the index and create a tree object of it. Cool. So I created a new object with this SHA-1 value. What do I do to make sure it's actually a tree object? Catfile -t, correct. So let's use git catfile -t bb096. It's a tree object. If I want to look at its content, I would use git catfile -p, correct? Cool. So we see here we have the cache info. Blob with this SHA corresponds to brief.txt. Cool. So I have a tree object. what would happen to git status at this point? Now remember, it's not only that I created a tree object, I also updated the index, correct? So this is a very weird state that you wouldn't encounter if you weren't playing with git comments like I did. So first of all, it says we have a new file ready to be committed. Why is there a new file?
Put it in the index.
Because it's in the index, correct. But also, there is a deleted file brief.txt. Why does Git think I deleted the file brief.txt?
Because you moved it out of the direct, whatever, the first space, and you went to the index. So
Okay, so it was in the index,
it's a new
but
SHA.
it's a new SHA, that's fine. It's a new SHA, it means that it's a new file. But why is it deleted? Because it doesn't exist on the file system, right? If I use dir now, I don't have this file, brief.txt. So let me create this file. There are different ways to do it. For this case, let's just use git cat file -p to get the content and write them into brief.txt. OK, so now if I look at the content of brief.txt, I have the file here. So git status now thinks that I have this file ready to be committed. Cool. And I have a tree object that I created. What would be the next step?
Git commit.
Create a commit. Correct. So a commit object points to a tree. Correct. By the way, before I continue, just to make sure it's clear, if you were to write, sorry?
I was going to say, you did lose me there. Just by typing git cat file, how was the file created? Like that was right.
No, I did git cat file -p. OK, so let's
Okay.
split that into two. OK, git cat file -p with the SHA-1 value. This gives me the content of the file. And now I just fed this into the file brief.txt. All right? OK, cool. So if I were to create this blob on another machine on another day to create this content, would I get the same SHA-1 value?
Is the timestamp part of the?
No. What did we say a blob contains? Only
The bytes.
the bytes, the contents, correct? No timestamp or anything like that. So if you were to create on your machine a blob containing this string exactly, you would get the same blob chop, correct? Now if you were to take that and create a tree on your machine, a tree that looks like that, would you get the same blob chop for the tree?
Yes.
Yes, because it would be the same. But now I'm about to create a commit. If you would create a commit, you will get a different commit object because you will have a different timestamp, probably a different author as well. OK, so a commit points to a tree object, correct? So let me take the SHA value of the tree, and I'll use git commit tree, which takes a tree hash value. And let's give it a message, initial commit, like before. And I got a new SHA value. Yes, please.
What happens with unreferenced blobs?
I can't hear you, I'm sorry.
Does Git deal with unreferenced blobs and trees, like objects?
Yeah, what happens with objects that are not referenced, do you mean? So there is something called garbage collection within Git. And when you have loose objects, after some time, it deletes them. And if you're interested, I can talk to you about it later. OK? Cool. So we created a new object. How do I know the type of this object if I want to make sure? Right, I can use git cat file -t 7106. So this is a commit object. Let's look at the contents. Cool, so we see that we have a commit object with the tree pointing to the SHA-1 value of our tree, with the author, committer, and the message. Cool. So now we have a commit object. What would happen to git status?
It'd be like, it's ready to push.
Right? Nothing really. Why? The fact that I've created the commit object somewhere in the internal database of Git doesn't mean that Git status is aware, right? In order for Git status to be aware, what do we need to do?
Git add.
We've already added it to the index before, the object, and we've created a commit object already. But git commit does two things. It creates a commit object, remember, as we did, and it also
Snapshot.
changes. It is the snapshot. That's the commit object. And also, it updates the branch, right? So right now, when git status looks on branch main, it's looking for main, which doesn't really exist. So let's create main. What is a branch? A branch is a
Tree of trees.
named reference to a commit. So let's create that. So I'm going to take the commit object. This is the SHA-1 of the commit object. And I'm going to use echo. I'm going to write this SHA-1 value into .git refs heads. Remember this folder?
Yeah.
Main. So again, just to be sure, let's look at our .git folder. We have the objects we created before. And now we have refs heads main, which is a file type git refs heads main. This file consists of the SHA-1 value of our commit object. And as a reminder, we take the first two characters. This is a folder within objects, and then the rest. Git status. So what is git status going to do? Let's try. Before we hit enter, what is it going to do? It's going to go to head, right? So it's going to go to the head, and head tells it, okay, go to the refs heads main. So it will go to refs heads main, and it will get to this commit. Git status on branch main, nothing to commit. Git log. We have a commit object with head pointing to main and everything that we've created from scratch. Cool. I want to create another branch, test, like we did before. How would I do that?
Make a new folder.
Yes, you have to make
Yeah, sorry?
The same way we just created the main by creating a new reference.
Exactly. So the same way as we created main, we'll write the same commit, but instead of writing it into .git refs head main, we write it into .git refs heads test. All right. Git log. Head is pointing to main, and we also have test pointing to the same commit. Again, branch is just a named reference to a commit, and now you know it's just a file within the .git refs heads folder. I want to change the active branch to be test. How would I do that?
You need to change where head is pointing.
Right, change where head is pointing to. So I want to write into head, I'm going to write refs heads test, correct, into .git/head. Git log, head is pointing to test. Let's create a new commit object. Okay, so from scratch, let's actually create a file to the file system this time. So let's write swim is awesome to swim.txt. So now I have a new file, right? I have here brief.txt and swim.txt. Swim.txt looks like that. Now I want to create a blob out of this. So I'll take the content and I'll feed it into git, remember? Hash object, correct. I want git hash object to take the input from the standard input and to write it to the internal database of Git. How do I validate that this is indeed a blob? Cat file minus T, thank you, 6802. It's a blob. Preprint. This is the content we expected, right? Cool. As a next step, now I have a blob. What do I need to do next?
Create a tree.
Update the, right, create a tree. And for that, I want to update the index. So git update index. And I want to add a new file, right? With the SHA-1 of this value. And we'll call it swim.txt. So now my index is updated. If I try git status, I'll see that I have a file ready to be committed because it's part of the index. And I want to create a tree object. So I'll use git write tree. Write tree. Cat file, just to make sure we know what to expect. This is going to be a tree, correct. Let's observe. So we have two blobs one for brief.txt, one for swim.txt with those corresponding SHA-1 values. Cool, so now we have a tree object. And now we want to create a
Commit file?
commit, correct. A commit object first. So I'm going to use commit tree. I'm going to provide this SHA-1 value, right? Now this is now not the first commit, but rather the second commit, which means that it also has a parent. So we need to specify the parent. Let's find the previous commit object. There it is. So I'm going to take the value of this commit object, minus p for parent, minus m, another commit, coffee, code and coffee. Cool. So now we have a new object, cat file minus t, 250c. It's a commit. It has a tree, and now it has a parent, unlike the previous one, right? Cool. Do I need to do anything else now? I just created a commit object, right?
Have you pushed it yet?
Pushed where? Not to a remote repository, of course, right? We're working locally. The commit object exists, but if I use git log now, what is going to happen? It's going to show me exactly the same thing, because it's going to go to head, and head points to test, and test points to this commit. So what do I need to do?
You have to change where the branch is pointing.
Correct, I have to change where the branch is pointing. So I'm going to take the SHA-1 of the newly created commit, and where do I write it to?
Main.
Not main, because I'm not on main,
On test.
on test, right? So I'm going to echo the SHA-1 of this newly created commit into git refs heads test. So now when I use git log, when I hit enter, Git is going to go to .git/head, which is a file that says refs heads test. That is, go to the branch test. Go to this file where we've just written this SHA-1 value, right? And from this SHA-1 value, it has a parent commit. So it can trace back to the other commit. So we got two commits where this one is on the test branch, and it points to its parent commit where main is still pointing to. And we've done all of that without using git add and git commit. Yes, please.
What happened if you added the second commit without specifying the parent?
So it would be a commit that would be somewhere, right? And if I were to change test to point to it, then test would point to this commit, and that's it. Test is just a name. If I just create another commit somewhere else and change test to point to this commit, test doesn't remember the other commits. It's not emotionally attached to previous commits, right? It's just a pointer to some commit object. Yes, please.
How exactly is this tree structure stored? Is it a linked list or a tree specific tree? Because let's say I have to go to 100 commits before. I'm assuming it will traverse to parent to parent to parent to the previous commit, right?
So again,
If I have to reference my 100 commit, like,
yeah, let's say you have 100 commits.
yeah, I'm assuming the only way it has stored it is via parent, right? It will go from this commit to the parent to the parent to the parent to
Right, so here I'm just using git log, correct? So to use git log, it will go from the first one that head is pointing to the branch, and then to the parent and parent and parent and so on. But this only shows the metadata for the commit object. That's it. Only when I check out a commit does Git go and actually fetch the entire working dir from that commit, because it would go to the tree object that the commit is pointing to, right? And then take the subtree and blobs that it references and the subtrees recursively.
Yeah, my question was around, is it pure linked list or is it like stored in some particular?
No, it's just stored as we've seen before. So when I go to here, we can see that everything is stored under objects just like so. And the way to go to iterate over the commit is by going to one commit, then going to the parent, and going again to the objects directory, just like so. No other structure or anything.
Stored in the
There is no other structure for it. The structure is a linked list of pointers for the parents, and to get the actual commit object, you need to go to the objects directory. It is a linked list, but it's stored not as a separate list, but rather the commit object has a reference to its parent, and then the parent commit has an object reference to its parent, and so on. Okay, cool. So let's see what we've covered this time together. So we started by posing a few questions, and we asked ourselves, why do we even care? And we said that as professionals, we want to understand how Git works under the hood. We said that it's cool. I hope that now you agree with me. We also said that it comes in handy. And also, I hope that now you feel more confident when you work with Git, as you understand the answers to these questions and a few others as well. We then went on to explain the different Git objects. We said that a blob is the contents of a file. We said that trees are directory listings of blobs and other trees. And that commit objects are snapshots of the working tree at a certain point in time. We also talked about branches and said that a branch is just a named reference to a commit. And now we also know that it's basically a file that resides within .git/refs/heads. We then talked about the 3 different snapshots within Git, or states: the working dir, the index or the staging area, and the repository, which is a collection of commits. And then we applied our knowledge to create a repository from scratch, including 2 branches and 2 commits. If you're interested in learning more about Git internals, you're welcome to ask me afterwards. You can also see some of the content that I post on my Brief Vid channel on YouTube, or follow me on Twitter. And if you're interested in learning more about Swim, please check out swim.io. I hope you've learned something new. Thank you very much, and feel free to come here afterwards and ask me any questions you may have. Thank you, everybody.